I will be explaining you Cayley's theorem for group in this video. So here you can see the statement. If A is an algebra, they are saying this A is an algebra. To say A is an algebra, there are some conditions also. I have explained that in another video. You can see that on my playlist. Okay. So here they are saying A is an algebra. Therefore, from this you can say this A is a vector space also. Okay, by the definition of algebra you can say that. So what they are saying, the statement with this algebra is having a unit element over the field F, then this A, what you have to prove is A is isomorphic to a sub-algebra of A of V. That is, you have to prove A isomorphic to A of V. That is what you are going to prove for some vector space B over F. So here first in the proof, in the first line what you are going to write is, you just copy it down. That is given in the copy it down from the statement. Okay, the first line you can see, if A is an algebra with unit element over F, just copy it down from the question and just write it down on the first line of our proof. Now given, you just write it down, and then by the definition of algebra you are writing the next line. In the next line you will write A is a vector space over, therefore A is a vector space over F. You are writing this line by the definition of algebra. Now here you have, in the statement they are talking about the vector space capital V, and here you have said by the definition of algebra this A is also a vector space. So using these two you can write in the next line this B equal to A. And now what you are doing is, you are defining a mapping. That is TA from V to V by V into TA is equal to VA. For all this V and A belongs to capital A. That is how you are defining this mapping. And now you are going to say this TA is a linear transformation. I told you in this theorem you are going to prove A isomorphic to A of B. Here rise a question, you may ask me, then why you are finding TA is a linear transformation? I have an answer for that question. So here, the reason for proving TA is a linear transformation is, you are going to prove this condition, right? So to prove this, you will take an element from A of V. The elements present in A of V will be the linear transformations. So that is why first you are taking an element TA. And you will say this TA is a linear transformation. After that, you will say that TA belongs to this A of V. This is a linear transformation, right? So I told you this A of V will have, the elements of A of V will be the linear transformation. So this TA, here you have proved TA is a linear transformation. From that you can say TA belongs to A of V. Okay, for that purpose only you are here finding TA is a linear transformation. I hope you got my point. And now here we are going to prove TA. This TA is a linear transformation. So to say TA is a linear transformation, it is enough to prove TA belongs to homomorphism of V, V. Now here you have, to prove this, we have two conditions for homomorphism. These are the two conditions. V1 plus V2 into TA is equal to V1A plus V2A. And the second condition is alpha V into TA is equal to alpha VTA. These are the two conditions. We are going to prove these two conditions. So first you have to take two vectors from the vector space capital V. That is what you are writing here. Let V1 comma V2, you are taking these two elements from capital V, that is vector space. Now consider the left hand side. You are going to prove the first condition. Okay, consider the left hand side of this first condition. So that is, you are writing like this is equal to, this can be written like this. How? You have defined like this, right? V into TA can be written as VA. This way, V and this A. Okay, you can write like this. Similarly, here you are having, consider this as V and this is TA. How can you write? According to this sentence, write this value into this value, right? This into this value. So that is what you are writing. Okay, now from this to this, you are just multiplying so that you will get this. So you have proved the right hand side. So first condition you have proved, and now we are passing on to prove the second condition of the homomorphism. So here you can see the condition. Take the left hand side of this condition, alpha v into Ta is equal to this also you can write using this condition. This is how you have defined, right? From this definition that you have defined, you are going to write like this. Alpha v, if v into Ta means, you can write this v and this a. Similarly, here in the place of v, we have alpha v. And Ta, you can write what? You write this into this value. That is how you are writing. And now you are writing these two elements in the bracket and keeping alpha outside. You can write like that, okay? Because alpha is a scalar, so that you can make this kind of adjustment. And now you are writing Va. Here you have Va. You can write Va like this also, right? So you are writing like this, alpha into Vta by our definition, right? Now you have proved the right hand side of this second condition also. So you proved two conditions of homomorphism. So from this you can say Ta belongs to homomorphism of V comma V. That is, if you proved Ta belongs to homomorphism of V comma V, means you have proved Ta belongs to A of V also. So if Ta belongs to A of V means, what you will know? Ta is a linear transformation of capital V. So you have proved the first part of this lemma. Now you are going to prove A is isomorphic to A of V. Okay. You can see that video in another you can see that in another video. Okay.